students, so far we have seen two applications of integral calculus, namely the application of integral calculus to find area and the application of integral calculus to find volume of revolution. Now in this presentation we'll try to see other applications of integral calculus, namely the application of integral calculus to solve problems related to work done by a force, and problems related to motion of a particle. Now, at the end of this topic, you are expected to find work done by a force on an object, and you are expected to find displacement, velocity, and acceleration of a moving body that moves in straight path. Now, the first one is work done. As you know, in your physics, work done is nothing but the area determined by force displacement, force versus displacement graph. In force versus displacement graph, area always represents work done. And as we know, area is nothing but integral from a to b of f of x dx. Therefore, work done can be defined as the integral from a to b of f of x dx. Now, for instance, let us have the following example. Find the work done when a particle is moved through a displacement of 10 meters along a smooth horizontal surface by a force F whose magnitude is 6 Newton. The force is a constant force, a fixed force. Therefore, area is nothing but, this is rectangle, area is base times height. Therefore, the work done will be base is 10, and height is 6, 10 times 6, it is 60 joule. Now, let us see the integral approach to work done. Work done is integral from a to b of f of x dx. Now, in our case, from a to b is from 0 to 10. My function f of x is simply 6 Newton. 6 dx, so I'll have the integral is 6x, evaluate this from 0 to 10, so I'll have 6, 10 minus 0, that is 6 times 10, 60 joule. Therefore, the work done will be 60 joule. Or simply base times height, because it is rectangle. Now, when the force is 9 minus half x, of course this is what? A trapezium. And we know that the area of a trapezium is half times base 1 plus base 2 times height. So, work done using ordinary formula is, it is area, but the area is, because it is a trapezium, half b1 plus b2 times height. Half times, what is base 1 and base 2? The two parallel sides. This is 9 Newton. And when x is 10, what is the height? Half of 10, 5, 9 minus 5, it is 4. Therefore, the two bases are 9 and 4. 9 and 4. 9 and 4. And the height is nothing but the distance between the two parallel sides, that is 10. So, half of 10 is 5. 9 plus 4 is 13, 13 times 5, that is 65. Now, let us apply the integral approach. Work done is the integral from a to b of f of x dx. Now, from a to b, in our case, from 0 to 10. And my function is 9 minus half x, okay, dx. Now, what is the integral? It is 9x minus the integral of this one, 1 over 4 x squared. Let's evaluate this from 0 to 10. So, 9 times 10 minus 0, minus 1 over 4, 10 square minus 0 square. 9 times 10 minus 1 over 4, 100 minus 0, it is 100. So 90 minus 1/4 of 100 is 25. 90 minus 25, 65 joule. The same result. Okay? The same result. So the work done will be 65 joule. Now, when f is 100 minus x squared, I think this is not a simple region, therefore we have to go through the integral approach. So work done is the integral from a to b of f of x dx, from a to b, in our case, from 0 to 10, of my function is 100 minus x squared, 100 minus x squared dx. So the integral will be 100x minus 1/3 of x cubed, evaluated from 0 to 10, 100, 10 minus 0, minus 1/3, 10 cube minus 0 cube. So you'll have 100 times 10 minus 1/3 of, this is 1000, 1000 minus 0, 1000. So 100 times 10, 1000 minus 1000 over 3, 3000 minus 1000, 2000 over 3. So if you like dividing 2000 by 3, we'll have 666.7 joule. So this is the work done by this variable force.